So now comparing the ideal and practical switch. Ideal switch block arbitrary large forward and reverse voltage with zero current flow when on, as we said earlier. But in practice, there is some finite value of blocking voltage, not zero, but some value with some current flow during turn off, which is called leakage. So ideally it should be zero, but in practice it's not. It has some finite value. Conduct arbitrarily large currents with zero voltage drop when on. We have seen the ideal characteristics, but in practice it's not like that. It has some value, finite value of voltage drop during turn on. It's not zero. It has some value. So that can be called as a threshold voltage. So switch from on to off or vice versa instantaneously when triggered. Means no delay. Whenever we say that, okay, switch on or switch off, transitioning from on to off or off to on, it should happen in zero time instant. But in practice, it's not like that. It actually requires finite time to turn on or to turn off. So very small power required from control source to trigger the switch. In general, yes, we can do that. We do not know the difference, but still we can trigger on these MOSFETs and IGBTs with a very small value of power. But some of the devices we need higher values of power, like GTOs, in practice. But ideally, all of these should be triggered with a very small power signal or control signal. In practice, it varies. No absolute values, but it varies from device to device. MOSFETs and IGBTs, they require very small amount of power signal for triggering. Others may require high values. So based on the differences between ideal and practical switches, so now we know that what are the parameters which makes the differences between ideal switch and practical switch. So this is the one reason which differentiates the ideal switch and from the practical switch. Practically, we have some power switching losses. So power switch losses, mainly these power switch losses are forward conduction losses, blocking state losses, and switching losses. Now forward conduction loss. So now this is the ideal switch, and this can be a practical switch. In ideal switch, zero voltage drop across it when it's on. When it is on, no voltage drop across it. And the forward current must be very, very high because we do not have any voltage drop. So the complete current from left to right will flow. No power drop over here. But in practice, the real switch exhibits some conduction voltage, on-state voltage. So means when this, let's say it is a this switch. So when this switch is turned on, we have some voltage drop across this collector and emitter. So between these two terminals, we have a voltage drop. That is the on-state voltage, because now the switch is on, and during that on state, we have some voltage drop. So collector and emitter VCE voltage drop, which can be for power electronic devices, it can range from 1 to 3 volts. So if we say that this is the voltage drop over here and the current is flowing through this switch with this voltage drop over here, it incurs some power loss. Current multiplied by the voltage drop over here, on state voltage. So that will be the power lost in this switch. Because what we want is whatever current flows over here, complete current flows over there without any power drop over here, just like in this ideal switch. So with this 1 to 3 volts of on-state voltage, this current gets multiplied by power in between over here, which is now a kind of a power loss inside the switch. So not the complete power will flow over here now. So this is called a conduction loss when it is on. So in this type, this conduction loss can happen mostly at low frequencies, starting from DC level. Now, the next type of loss is blocking state loss. This is a loss, a power loss when the switch is turned off. Because when the switch is turned off, the switch blocks large voltage. So in on state, the switch was having a voltage drop of 1 to 3 volts. During off state, the current will not flow directly like this. Infinite voltage is there, then no current will flow. But it has some finite value depending upon the application and the switch. So during off state, the voltage across this switch is very large. So due to that large voltage and a very small leakage current will flow due to the minority charge carriers, they get multiplied and we get a power loss. So due to that leakage current and a large off-state voltage, we get a leakage power. So, but if the leakage current is very small in microamperes or in nanoamperes, then the total power loss can be in microwatts. If the off-state voltage, let's say, is 1000 volts and the leakage current is about 1 microamperes, then 1 microamperes multiplied by 1 kilovolt is equal to about milliwatts of power. So that can be neglected in large power electronic applications. So off-state power can be neglected depending upon the application. For mobile phones, this milliwatt of power cannot be neglected. But in that case, we do not have a large value of voltages across off-state devices. But if we have number of switches running in a device, in, let's say, laptop or in other device, then this off-state power loss or a blocking state loss can be added or summed together. So it can cause substantial off-state power loss. In that case, we have to take care of that. Now the third type of loss is, first was the on-state loss, conduction loss. Another one was the blocking state loss, which is the off-state loss. Now third one is in between turning on and off or turning off and on. Switching loss. The switch can be transitioned from on to off or off to on. So that transition loss is a switching loss. So ideally, the transition time should be 0. That instantaneous switching on and off should happen. So if the transition time is 0, instantaneous switching is there, then power loss due to that instantaneous switching is 0. But in practice, there is always a transition time. So that transition time will cause a switching loss, because voltage takes some time to fall or grow or rise, or current also takes some time to rise or fall. So where they both cross each other, we have a switching power loss. So if these switches are transitioning at a very high speed, at a very high speed, then it means that a number of transitions happen during some particular time instant. So in that case, we can say yes, that switching loss can happen in high frequency operation. So these three types of losses are there in these switches used in power electronics. So due to these switching losses, on-state losses means conduction losses and off-state loss, the efficiency can decrease if these losses are substantial. So we try to minimize these losses so that the efficiency becomes higher. Graphically, we can show over here. This is the on state, the switch is on. Sorry, in this case, this is a voltage signal over here. And in on, the voltage is very small value. So in that case, this is off state. The off state of a switch has a voltage of this value and a current of this value, leakage current. This is during off state, there is a leakage current due to minority charge carriers. So this thing you have to remember for always. So this is the power loss, V multiplied by I during off state. During on state, this is a transition from this, now switch is now changing its state from off to on. So this is on state. In between off state and on state, we have a transition time period. So during this period, the voltage starts to fall and the current starts to rise. And at this instant, we have a power loss, V into I, that is substantial. And this is the switch turning on now. In this case, the switch is turning on. We have a very small value of on-state voltage, 1 to 3 volts in power electronic switches. And a maximum amount of current is flowing depending upon the application. So now this on-state power loss is conduction loss, which is IC multiplied by V. If voltage is very small in value, the conduction loss over here can be less. Only the transition loss is maximum at this point, where we have a cross section of voltage and current signals. We have a maximum value of transition or switching loss. So blocking of loss is very small, followed by a transition loss, which becomes higher at that particular instant. And then the conduction loss, which is having some value, finite value, greater than the off-state loss, which is turn-off loss. So, and these two losses during turn-on and turn-off, they can be combined together to make a switching loss. This is also a switching loss. This is also a switching loss. So they need to be summed together for that particular time cycle. So sum of all these losses, they play an important role in calculating the efficiency of these switches. So these losses should be as low as possible for high efficiency applications. Operating states of switches, again, we know that two states, a third state is commutation, the transition state. So normally stable states, this commutation state is not a stable state. It is a transition state. So the two stable states are possible in any switch, on state and off state. Transition is always a transition phase, which is not stable. It has to change. So in that case, we can say two stable states and one quasi-stable state. So during on state, we have, for on state, we are concerned with current ratings. So DC continuous current rating and average rating, RMS, peak ratings, short circuit rating. In on state, there is some on state voltage, also called residual voltage, VR. The loss during on state, as we saw in earlier slides, is ION multiplied by R, that particular current during on, and that residual voltage means on state voltage. So if we multiply these two, we get an on state loss. This duty cycle, we need to consider that for what percentage of the time cycle this switch was on. We'll see that. In off state, we are concerned with voltage ratings. In off state, we know that, okay, residual current flows. In off state, again, the same thing, off state voltage multiplied by the off state current. We get an off state loss, as we said in the previous slides. So in this case, the duty cycle is 1 minus D. If during on state the duty cycle was D and total time is 1, let's say one time cycle is 100%, which can be normalized as 1. So D was the time, a duty cycle during on state, and 1 minus D is the duty cycle for off state. So this is an example over here. So this is a 2-pulse rectifier. The load current is 50 amperes. The device has a forward voltage drop of 1.5 volts when on. Leakage current is about 1 milliampere during blocking voltage. During reverse bias, it is 1 milliampere leakage current during off state. So we need to compare on state and off state losses. We know that during on state, the loss is current during off state, or during on state, and voltage during on state. Multiply these two together for how long this switch was on, which is denoted by duty cycle D. So we need to multiply this. So 50 amperes was the current, on state current, and 1.5 volts is the on state voltage. We multiply these two. Now from here it says that it is on for 50% of the cycle, and for 50% of the cycle it is off. So for on state, value of D is 50% of the total, so which is 0.5. So D is 0.5. So 0.5 multiplied by 75, we have 37.5 watts. So on state loss is 37.5 watts. What is the off state loss? So the off state loss is 1 minus D multiplied by the leakage current multiplied by the off state voltage. And 1 minus D is 0.5 because 50% duty cycle it is off. So 0.5 multiplied by the leakage current multiplied by the off state voltage or blocking voltage, which is 0.2 watts. And off state loss is very, very small compared to the on state loss. So we can neglect it. So we can calculate the value of on state losses, means conduction losses, or off state losses. Now commutation. Commutation can cause switching loss, which we saw in the earlier slides. So this is the third type of a loss. Two types of losses we have actually calculated. Conduction loss means on-state loss, and off-state loss is a blocking loss. And the third type of loss is a switching loss due to transition. During commutation, means to turn on or turn off, we go into transition phase, means the switch goes into transition phase. And during this transition, a switching loss occurs. So during this time period, it takes some time to turn on and turn off. From here, the switch was turned on, and from turning on to turning off, it takes some time, and turning off to turning on, it takes some time. Just to be familiar with that, which is the fast transition, means fast switching and slow switching. It takes some time. There is a delay from this state to this state. And for this one, there is no delay. Instantaneously, this signal falls from high value to zero value. So the transition is very fast, in zero time, ideally. But in practice, it takes some time to rise, and it takes some time to fall, causing slow transition. So now, in detail, how to understand the turning on mechanism of a SCR, because we will be dealing with SCRs as a switch in most of our power converter circuits. And this is the main switching device used in power electronics in almost all the applications. The time taken for SCR to traverse from blocking state to conducting state. Yes, we know that. This is called turn on time. And this turn on time is divided into 3 time periods. One is TD, which is delay time. TR is the rise time. TP is the peak time or spread time. Okay, so T on, which is sum of delay time. So in this case, this is a delay time over here. Delay time says that this current over here, it reaches from 0 to 10%, the anode current. The anode current reaches from 0 to 10% in time period called delay time. So the time taken by the anode current to rise from 0 to 10% is called delay time. Similarly, the time taken by the gate signal to rise from 90% to 100% is called delay time. Okay. Now, rise time. So rise time is the time taken by anode current to grow from or to rise from 10% of the anode current to 90% of the anode current. Or in other words, the time taken by the voltage, anode voltage, to fall from 90% to 1%. Simple. So anode current rises from 10% to 90% is called rise time. And anode voltage falling from 90% to 10% is also called rise time, because rise time is for the current to turn on, and for turning on, the voltage will drop. Okay, further now, because we need to have 100% of the anode current. So time taken by the anode current to rise from 90% to 100% is called peak current or spread time, or peak time or spread time. The same over here. Now the voltage is falling from 10% to 0 value, called on-state voltage. 0 value means from 10% of voltage, anode voltage, to the on-state voltage. The time it takes is peak time. And in anode current side, the time it takes the anode current to rise from 90% to 100% of the current is called peak time or spread time. So, and now this anode current is fully flowing in the device or in the circuit, like load current and also. And now the voltage is now steady state in that particular SCR to a on-state voltage, which can be 1 volt to 3 volts. So that on-state voltage is there in the device, 1 to 3 volts, also called residual voltage. And current now continues to flow in the circuit at 100% value. And about the power loss also becomes steady state because on-state voltage settles at 1 to 3 volts. The maximum current settles at some maximum value depending upon the value of current in that particular application. And now multiplying both of these, we get a on-state power, conduction loss or on-state loss. Now this switching loss, it starts to build up from 10% of the anode current to the 90% of the anode current, which happens during rise time. And during this rise time, we have the voltage dropping from 90 to 10%, and we have a high value of switching loss. So now after this steady state, this now load current or the anode current is in steady state. So let's say now we have started to turn off this device with commutation, forced commutation or natural commutation. So this now rate of change of current will happen through anode. So this rate of change, if it is fast, rate of change of current or rate of change of rate of fall of current, if it is fast, we say it's a fast transition. If it is slow, we call it slow transition. So depending upon the rate of change of current during falling of the current, because we are now turning off this device from here. Now this device, this anode current comes to 0 value. So at this point, we can say the device is turned off because the anode current becomes 0. But due to the charge carriers, a large value of charge carriers accumulated in the capacitances in the junctions, we have a large inflow of the minority charge carriers on the other side, in the negative side of the current, due to inertia of all this. And now this takes some time for recovery. So here the charged carriers are recombined and settle down. So all these minority charge carriers take some time to recombine. So that time taken for recombination of these charge carriers is called reverse recovery time, same as in diode. So after this one is turn off mechanism. So after this, it takes some time to remove further charges with recombination from junction 2. So these are the sweeping out of the charges. This time period, we need to sweep out the charges from junction 1 and junction 3. And in junction 2, because in junction 2 also there are charge carriers accumulated. So we need some time to recombine these charge carriers or to sweep out these charge carriers. So this is called gate recovery time because junction 2 is connected with the gate. So after this reverse recovery time and gate recovery time, we can say now the current becomes 0. Now this device can be ready for the next on cycle. And then the complete cycle again repeats itself. So now the forward blocking of the device is possible at this point. So from here we can say that the transition losses over here turn on, and this is the turn off loss, which is not shown over here. And both of these losses are summed together for calculation of switching loss. So now gate triggered driver circuits and protection circuits, and we know that for all these devices, controllable, fully controllable or semi-controllable devices, we need to trigger the gate circuit. We need to trigger the gate terminal. So this is a control circuit over here, which controls the driver circuit, which in turn activates the gate terminal over here. What are the functions performed by this? Amplification, depending upon the value required over here, depending upon the amplitude of a control signal required here, we need amplification. Isolation, because this switch can be connected to a high power circuit or high power load. So all these high power signals cannot cross over to these low power electronic circuits. So we need isolation for that. So this complexity of this control circuit and driver circuit varies among various switches. So for MOSFET and IGBT, IGCT, it is very simple. For GTOs and BJTs, this gate drive circuit or gate control circuit is complicated, complex, and expensive. Okay, one example here we can see that this is a switch, a MOSFET, a power electronic switch. So we are driving this power electronic switch using this circuit. So this VGS is normally used to switch on or switch off the device. When we apply 15 volts over here, this device is turned on, this switch is switched on. And when we remove this VGS, means 0 volt, is when there is 0 volt across this gate terminal, we have switched off this one MOSFET. So when this B1 is high, let's say, high means 15 volts, let's say we are supplying 15 volts. So 15 volts are called as high signal and 0 is called as low signal. So when this B1 is high, Q1 starts to conduct, this transistor starts to conduct. And if it starts to conduct, VGS now pull to 0, because now this switch is conducting. When this switch is conducting, this VGS goes to 0 value. So making the MOSFET off. Now when B1 is connected to low, this Q1 switch is off. And when Q1 switch is off, this switch is off now. This VGS is connected directly to the 15 volt over here, because this one is off. So this is pulled high. So if this is pulled high, so we have a 15 volts across VGS. So when there is a 15 volts across VGS, the switch is turned on. So just by switching this transistor on and off, we switch this switch on and off. Very simple. So no complicated control circuit, gate control circuit is required in MOSFET firing or MOSFET switching on and off. Now snubber circuit. So when we connect this switch in any circuit over here, we have a circulating current due to this stray inductance created in any wire or any wire in a PCB. So we know using KVL, we get this value of VCE, this VCE, which is V in plus the voltage drop here. So the voltage, the turn off voltage, during turn off, the complete voltage, this plus this is applied across here. So which actually creates an overshoot over here, a complete overshoot, because all of a sudden, due to this stray inductance, the complete voltage is applied. When all of a sudden we turn off this device, this switch, all of a sudden overshoot happens, which may destroy or damage the device. So we need to protect this device from these surges or these overshoots. How to do that? We need to connect a snubber circuit. So this snubber circuit, so you know that when this current flows, if this is forward biased, this diode, the current will start to flow here because this switch is turned off, posing high resistance to the current. So the current will not follow this path. Current will follow this path and it starts to charge this capacitance. So whatever surge we have over here is applied to this capacitor, which was initially uncharged, now it becomes charged. So now this capacitor will act as a kind of a snubber. It snubs the overshoot. So it kind of a shocker. So it smoothens the overshoot. So all the overshoot will travel to the capacitor. It will not travel to the device. It travels to the capacitor through forward bias diode. So now this capacitor is charged with this overshoot. So whenever we need to discharge this capacitor, we cannot do it through this diode because it is reverse bias now. So we need to go through this path, which is resistance. So this resistance will, you can say, dampen the high charge over here. So this to limit the current. This resistance will be used to limit this current. So a smooth current will flow over here, or a smooth current to charge the capacitor. So this RCD in both directions will smoothen the transition, will smoothen all these surges or overshoots. So in reality, with snubbers, without snubbers, this is the actual waveform of voltage. With snubber, we have smoothened these overshoots. So now we do not have any dangerous effect on this switch. So, okay, during turn on, large overcurrents are minimized. During turn off, large over voltages are minimized. So with this, we come to the end of this topic. We can do more examples on this. We can do 1 or 2 examples on this topic in tutorial sessions, and then you will be able to understand that how to numerically analyze these devices in power electronic circuits. Okay, thank you.